Okay, so this problem has to do with compound interest, which they already gave us the compound interest formula, and we already know what it all means. But for some reason, they talk about what A and P and R and N and T mean again. So anyway, that's what it is. So it says, how long will it take $50,000 to grow to $1 million at an annual rate of 9% compounded monthly? Okay, so we have all the information except we don't have T. That's the how long part. So we're looking for T in this equation. Okay, that's why it's in this section. All right, what do we want in the end? What's the amount we want in our account? We're going to try to retire and we want $1 million. Okay, great. How much money are we starting with? What's the principal? So this is the A. What's the principal? 50,000. That's what we're starting with. So we're going to put $50,000 in an account. And we have 1 plus, now what's the rate of interest? 9%. So that's 0.09. And then how many times are we going to compound it in a year? It's compounded monthly, so N is 12. Oops, 12. And then we're going to raise that to the N times T. So that's 12T. So remember the N appears twice in the calculation. Okay. So first, I don't usually do this, so I'm not going to. The book switches it the other way, but I'm not going to. I'm going to be a rebel. Okay, we want to solve for that t that's up in the exponent. So this is an exponential equation. First thing we've got to do is get that exponent part by itself. Now in this case, the exponent part is this, okay? It's just something to an exponent. Okay, so I'm going to divide by 50,000. Oops. 1, 2, 3, 4 zeros. Okay. Now, I'll show you a little trick. When you have a bunch of zeros like this and you're dividing, it only works for zeros. But if I have 4 down here, then I can cross out 4 up here. Okay? So now I have 100 over 5, which 5 goes into 120 times. Or you can put all this in your calculator with all the zeros and you'll get the same thing. Okay. And then those 50,000s cancel. So I have 20 equals 1 plus. Now, I'm going to go ahead and divide this out. By the way, I know it's not going to be a repeating decimal. I don't normally do this. I usually put it all in the calculator, but I'm doing this because it'll make it a little bit easier to write and put in the calculator, and I'm not getting a repeating decimal. So 0.0075, and that's to the 12t. Okay. 0.0075, yeah. Okay, so, well, I can add those. So let me do that. 20 equals 1.0075 to the 12t. Now, if that fraction part, this part, if that had been a repeating decimal, I wouldn't do it. I would just leave it until I got to the very end and I had to put in the calculation. But this time it's not a repeating decimal, so it makes it a little bit easier in the writing. Okay, so here we go. We want to solve for t, right? Okay, the base is not, this is the base, it's not a power of 10, so we're going to take the natural log of both sides. Okay, so that's great. That's what we want to do. We're going to take this exponent, and it's all of this down in front. So natural log of 20 equals 12t times the natural log of 1.0075, which is just a number. Okay, so I'm trying to solve for t. Now I want to switch it the other way. Okay, 12t. You really don't have to, but I'm just gonna do that for some reason. Hopefully I didn't miss a 0, so. Okay, and I'm gonna go ahead and put parentheses around the 20. I'm gonna need it when I put it in a calculator anyway. Okay, now remember the 12 is just a number and the natural log of 1.0075 is just a number. So we are going to divide by both of them because we're trying to get t by itself. Okay, whoops. Okay, so the 12s cancel. The natural log of 1.0075, those cancel. And so I have t equals. Now, here's how it's going to go in the calculator. You're going to have the natural log of 20 divided by, and then you're going to have to open a parenthesis, 12 times the natural log of 1.0075, close it, close it. Okay? And this is going to be approximately, okay, go ahead and stop the video and do that on your calculator and see what you get. Okay, so I got approximately 33.41. So it takes about 33 years. So if you were 20 and you put $50,000 in this account that did this, had 9% interest compounded monthly, then in 33 years you'd have $1 million. You could retire and, well, that'd be great. I missed that boat. didn't set any aside of any money when I was 20. So, but they say if you want to retire someday, invest early because that makes the difference. Okay. Anyway, that's a little bit about retirement and how your money grows in compound interest. And there you go.